Hello everyone, this is lecture 6. First topic, compilation process in FORTRAN. So last year this was shown at lecture 4. The compilation process, it's the process of converting your source code to the executable. Those are actual commands to the processor to do the calculations. Remember we talked about we're using computers to crunch numbers, to compute. So we're giving instructions to the processor to take some numbers, crunch them, print them out using the operating system. So back to the compilation process. It starts with the source code. Here it says F08 extension file. We don't use that. We use more standard F90 extension. The source code is something that you write, or we write together. It goes into compiler. The one that is installed in Cygwin, or the one that comes with Linux. There are other compilers. There is one modern compiler produced by Intel. So the compiler takes in the source code. And here in this flowchart, it shows that it checks for errors. The arrow kind of goes down here. Is there any errors? And yes, it's possible to write the source code with some errors. Those would be called syntax errors. It will go outside of the syntax of the language. So compilers, it's also a program that crunches numbers using a fixed algorithm. So if it sees something that it cannot crunch, it's a syntax error and nothing can be done. If there's no syntax errors, something called the object code is produced, the .o file. Now we haven't seen those yet because in the standard default way that we run GFortran, it kind of bypasses that stage. Of course, it performs that stage internally and it doesn't save those object files, but we'll talk about what the object files are. The object files go into the linker. Now again, we didn't see the linker yet because GFortran already has the linker in it, or at least it invokes the linker. The linker checks if there's any linking errors. We'll talk about that. And then the executable is produced. .o is not always .o extension, or at least in the past it hasn't been. Okay, so what is an object file? Object file is the binary file already. So your source code, the way that you've written in text, is compiled into processor instructions, into those binary codes that processor will execute. Object file, however, is not ready yet to be loaded in the processor. It's missing a lot of things in it. What is it missing? So it might be missing instructions for the operating system, how to load it in memory, where to place it in memory, how to pass the control to the CPU. So it just doesn't have all that. It just has like your code compiled, but the operating system is still needs a few more things for it. Maybe your code invokes something that's not present in your code. Examples. We used sine function. We used exponent function, write, read. Those are all functions. Now they're part of the kind of like a standard FORTRAN library. We can use them, but they're not in your source. So the moment you compile your source, even though those functions are invoked, they're not present in this single source file that was compiled. Somehow those object files, they're missing external functions that were called. They're missing some information for the operating system on how to load and how to use that object file. Also, it's possible for the object file to not have a starting point for your program. The programs that we wrote so far, all of them had like a statement that the program test, there is some code and then end program. So that will be a point where the program will start to execute. It is also possible to write some code that will be a function that somebody else has to call. That can be in the object file as well. We'll do all this right now. Let's talk about linker. So linker, essentially it produces the final product that can be somehow used by the operating system. So far we produced executables. Executables are picked up by the operating system, Linux, Windows, something else, and the operating system knows the layout of that executable file. It knows what to do with it. It knows how to give it to the processor to run. Executables can be produced not just by FORTRAN, but by other compilers, C and C++, even like written in Pascal. Executables can be produced in many different ways. And let's see how things used to be with FORTRAN. Back in the older system, the PDP-11. Code already prepared. This is the actual main program. It has a loop from -100 to 100. That integer then is converted into a real. So a would be a real, it's assigned to I. And then a is assigned to some function. The function is called f2. And there's a parameter of the function I divided by 100. It will go through the values from -1 to 1 with the increments of 100. The result is then printed. Now, this type command is the way to print out things on the screen. Over here, 200 is a label for the format. The format is given just right here below. The format, remember we talked about the format strings. If you still don't know format strings in FORTRAN, study them independently. This one will print out a floating point value of the total length 12 with at least 7 decimal points. And then finally, just like to conclude the program, to make sure everything runs, it just prints out another line. It's RT11 FORTRAN 4 version 2 demonstration test. Now keep in mind, this is the old syntax. This is the old FORTRAN 4 with a standard from 1966. By the way, this editor has an amazing feature. It has this help instruction. Many of those buttons, like this gold button, we don't even have anymore on the keyboards. So for me, it's a little bit of a struggle to type those. And then there's more instructions on the commands. Exit command will save the file. We're gonna try to exit. I have to type something here. Now I type the command exit. File is saved as test2 FORTRAN. There it is. There is another file that's already prepared. Let's show it. The function is fairly simple. It takes one parameter that is real. It checks if it's equal to 0. If the input parameter is 0, the output is also 0. Otherwise, it computes the exponent of -1 over 5a squared. The main program is written in one source file, which is test2. The other, the function is in another source file. Now this split is done for a reason, so that some functions can be shared, maybe with other programmers, maybe with other programs. So now that I have written this function f2 in a separate file, pass the source file to somebody. But we're talking about object files, so let's create one. We're going to invoke the compiler by the command ru for run. FORTRAN is the compiler on this RT11 system. We'll compile this last source code and we'll produce the object file tf.ob. What it prints out is f2 is the contents of what it found, like what functions it found in source. Let's now see if there is this object file, and indeed it was created right there. So we have this tf.object. It is a binary file. If we try to type it, we will see some sort of gibberish because it's not even meant to be human readable. Now let's compile the other one. Same instructions. we'll compile test2 into the object file test2. So this is the old syntax. It doesn't have this program name instruction. It just starts, okay, just do this. Start with a loop, and we're gonna go from here. So it's implicitly called main. This will be like the entry point. So far, we don't have the executable yet. So we have those two object files, the compiled sources into the binary. None of them can be executed. In order to produce the executable, we will need to link them together. There is another object file that is listed in this file directory. It's called forlib.obj. Now that contains the binaries for the functions such as sine, cosine, exponent, and so on. And we used exponent, so we really need it. We also used write statement. Write statement is a function. It's contained in this additional FORTRAN library. So if our objects are not linked to that, something will be missing. And let's just illustrate the linker error. Let's illustrate what will happen if something is missing. So we will link test2 to forlib. And remember, we use this f2 function, which is missing right now. And the linker, indeed, it's not very verbose. It doesn't really explain things. This software is very old, but it says there is the linker error, or maybe it's even a warning. Undefined globals f2. Let's do this properly now. Let's link our test code, the compiled object file. We also have the function and the FORTRAN library. Let's run. And we have the output as intended. Even in the 70s, this process was already understood that you don't jump to the final executable right away. First, you compile each of your sources into the object file, and they can be multiple pieces. Then you link those pieces together. Another reason for that is some programs can be fairly large. You want to split them naturally. And every time you edit something, you don't need to recompile this whole thing. So if you're working on the smaller fragments, say like one function, then you don't need this whole package to be compiled. And the whole thing may be big. Like now we have, for example, the Google Chromium browser. It takes 90 minutes to compile, even like on modern hardware. Even these days, this makes total sense to split the project into smaller pieces. Now these numbers I copy-pasted into LibreOffice like before, and of course this is the output. This is the plotted result. This is what we expected. This is what the function looks like. Just a little side note about this function. So it's exponent of 1 over x squared, in our case 1 over 5x squared. Let's look at this multi-step process in Visual Studio Code. So we will be looking at the practice problem set. There's 3 problems, and then the first problem goes like this. So analyze the problem in terms of input and output, develop an algorithm to solve the problem, write your algorithm in FORTRAN, compute and display the period of an oscillating pendulum in seconds as given by the equation. Now this equation, again, it looks big and scary. This is what's called the Taylor series expansion of the formula that you were given on the actual problem. So in many respects, this formula will produce the same output as the other one that you're given, with the difference that it will only be the same output in a very narrow range around the length of 1. So that's discussed later. So L is the length of the pendulum in meters. G is the acceleration due to gravity in meters per second squared. The formula is only applicable in the range from 0.9 to 1.1. If you go outside that range, the formula will produce erroneous result. Let's put it this way. So we have to limit the algorithm to this range only. So for this large equation, it's your job to convert this to FORTRAN code. For me, it's a little bit easier. I have Mathematica. Okay, so in Mathematica, there's a function called FORTRAN form. You give it an equation like this, and the result is FORTRAN code that's produced. I split it into several pieces, so each term is shown on each line, on separate line. And we start with this function that computes this long formula. So right now, we don't have any limitation on its input. We can even give it negative inputs. We can give it outside our intended scope. This is the function. It's called PR1, practice 1. L is the input. Result T will be the output. Pendulum period T. Implicit none instructs the compiler not to create any variables implicitly. So all variables used in code must be declared. This is especially important for the constants pi and g. If we forgot this line, and if we did not have implicit none, the first time it would see pi, it would think, okay, this is the variable, we'll implicitly create it, we'll assign it some random value, and then this formula would be computed, and the result would be not a number, because I already ran into this error. So implicit none, it's a very important instruction to the compiler that prevents errors. Now we assign those constants. Remember that parameter modifier means that those variables will actually be constant and they cannot be changed. And before we jump any further, in this same file, I will attach a little test program. This is not yet the answer to our assignment. The test program does not take anything from the user. Instead, it just loops around a fixed range. The integers go from -10 to 10, so 21 integers will be assigned. It converts k into the real, divides by 100, and adds 1. So our range is, as shown here, it's from 0.9 to 1.1. And then we print out the results of the function, but we also print out L. So we print out what we give to the function and the result of the function output. And over here, maybe another sort of reminder about the format strings. So we do have a format string. The first formatted value will be floating point, 6 characters total size, total width, with at least 2 decimal, actually at most 2 decimals are printed. Then we have some space, and the next one is 15 total size with 7 decimal places. So that's the result of our function. Of course, the assignment asks for different things. So the assignment asks you to request something from the user, check the boundaries. First, let's see how this code runs. This program is pr1.f90. We will compile this using gFortran. pr1.f90 output pr1. This will produce the executable as we did before. It already runs. This will already tested. And in our list of files here, we see pr1 executable. For now, I will delete it. And I will also remove this testing code, this testing main program. Now we will compile the source code into an object file. For that, I will add a switch to gFortran which will go like this, -c. So gfortran minus c. Then the name of the source. And that's all. Compile. We see there is a file that appeared, pr1.o. This file is not displayed in the editor because it's either binary or uses an unsupported text encoding. It is a binary file. There's really no point in trying to see it. Let's still see it. So there it is. It is indeed a binary. We can try to see it as some sort of binary file. So this is what's produced by a compiler. There's some interesting text strings mentioning the operating system and the version of the compiler. It's more like a version of the compiler. There's a way to see that in more like every symbol is encoded as a hexadecimal integer number. And the question is now, okay, so we do have this object file, but now what? And to use the object file, we'll need to link it to something. So here is our process. Let's link it to the other file that's here. It's t7.f9. And this is more like the practice problem question. Now it's very short code. It's very simple because our main difficulty has already been resolved in the other file. We have two variables. They're both reals, the length of the pendulum and the resulting period. We ask the user to enter the pendulum length. Remember this format string. So advance equals no means there will be no new line. And A just means like an array of characters. We read the real variable L, and we compute the period using pr1 function and print out the result. So far, there is still something missing. In particular, we did not put this limiting frames on the input. But let's try this. Let's see if this works. T7.f90. And indeed, another object file is produced. Let's first try to take t7.o and produce the executable output. Now, we already know we will have the linking error because pr1 is nowhere to be found. And indeed, in this case, the linker is much smarter than the one that from the 70s. It actually gives an error. It cannot produce the executable. Now let's include pr1 object file that we have. Indeed, the output is produced. Enter pendulum length 1.3. We know there's no limitation. And then so finally, let's just put the finishing touch on the program. We'll do this if the red value is not on our range. So if L is less than 0.9 or L is greater than 1.1, then we'll just print an error. So what happened here is that we reused the old object file that we previously compiled. But even though we changed the source file, we did not recompile the object file. So we still got the old code. And of course, the fix here is recompile the source first to produce the object file. Then produce the executable from the object files. And then run pendulum length. The length is out of range. By the way, if you don't want to enter the input parameter all the time, every time by hand, there is a trick in Linux, and it will also run in Cygwin Windows. it goes like this. So echo $, whatever input you want to provide, 1.3, then vertical line, and then run the executable. So now you have a line which will automatically enter the pendulum size. Let's discuss the hexadecimal system, which you have on the lab problem. In the hexadecimal system, instead of 10 digits, you now have 16. We don't have really more numbers to denote them, so we use A, B, C, D, E, and F. A for 10, B for 11, F for 15. We don't need 16 because we have 0, so that makes it 16 total. The numbers can be now written as a mix of letters and numbers. A01, B55, ABCD. Now let's convert the number BEEF. We begin with F, that's 15, multiplied by the base 16 to the power of 0, plus the next symbol. The next symbol is E, which is 14. We have the base 16 still, but it's the second digit. Third digit is the same. And the fourth digit is B, which is 11. Calculate. 48,879. Let's now take a look at another practice problem. Number 2, write a FORTRAN program that, given 3 points, x1, y1, x2, y2, and x3, y3, obtained from the user, computes and displays the equation of a parabola passing through these points. It can be done with a pen and paper. It can be done in Mathematica as well. There is a function, which is a quadratic equation, defined with A, B, and C, unknown right now variables. We will just solve the system of 3 equations. So function of x1 will be equal to y1, and so on. In this case, x's and y's are given, and we're just looking for A, B, and C that fit these conditions. And they're obtained as these expressions over here, of course. Not all values are acceptable, especially x's. They should be different. If some of the x's are given the same, then it will be a vertical line, which in this case, we're looking for a parabola. This is not going to work. So you can see they appear in the denominator as differences. And if any of them are the same, you'll get a denominator of 0. There will be a division by 0. I can convert those formula into FORTRAN expressions. This can be converted by hand, or this can be done automatically in programs such as Mathematica or MATLAB. One of the students asked me to do more practice in Windows. This is what we're gonna do. We will use Windows for this task. In Windows, we will use Visual Studio Code. Let's just make it full screen. And the program is already written. So this time we will not program anymore. We will just explain everything. And so this is the solution. It essentially it computes A, B, and C with the formula that we just created. Before it gets to that, it will need user input for x1, y1, x2, y2, x3, y3. We declare all the variables in the beginning of the program. They will all be reals, so there's x's, y's, and A, B, and C. The program asks the user to enter those numbers. We read them from the user input, convert them into A, B, and C's, print them out in the form of a quadratic equation. Notice the format string over here, so there'll be exponential notations. This is a placeholder for A. Then it will go like this, times x squared plus the next term b times just x, and plus the constant term c. Let's run it. It's already compiled. We're going to supply the user inputs with our echo command that we just discussed. And indeed, the quadratic equation is produced. That's all that's required for this task. Let's go and look back again at the PDF file. In your problem sets, you're asked to give an equation of a line. That's a little bit different. First, it's in a way easier because there's only going to be 2 points. And it's also a little bit harder because it may go vertical or it may go horizontal. And since we're on this already, let's jump to question number 3. It's particularly interesting. It kind of resembles the problems with the toll bridge that you see in problem set 2. There is also a sum that is required to be computed, also from problem set 2. So let's give it a look. The weight of a vehicle in tons is denoted by W, is a weight. A toll bridge charges 20 times the exponent of -1 over W squared. Remember, that's the function that we just discussed earlier in the lecture. That's the one we programmed in the older FORTRAN. So a toll bridge charges this amount for passenger cars. Here E is Euler's number, so essentially that's the exponent function. Trucks and buses are charged 10 large pi of 0 as the first parameter, W over 10 as the second parameter, where pi and k denotes the complete elliptic integral of the third kind. Now, if you did not see complete elliptic integrals of the third kind before, it's okay. This is a practice problem. There will be no complicated mathematics on the actual problem set, and you already have the problem set, and mathematics is simple enough. The reason for this elliptic integral is to show you how to address the problems that are seemingly difficult. There is no function in FORTRAN, there's no built-in function that will give you this elliptic integral, but we will search the internet and there will, of course, be one. Finally, cyclists are charged a fixed amount, which is given to you as this sum. Again, the task is to try to find the value for this sum. Of course, you could use other means to calculate this sum and get your constant number and then just program it into your program. The learning goal here for FORTRAN is to make a do loop to add the terms together. There is 2k factorial, which is put here on purpose. This example will show you how to get the factorial function in FORTRAN. You can, of course, write one on your own. There is no problem with that. You already know how to do that. It's going to be a loop that will multiply the numbers from 1 to k. In this case, there will be a trick that will be shown to you how to avoid programming your own factorial function. All fees are rounded to the nearest 25-cent increment. Why not? If a vehicle weighs more than 9 tons, it's not allowed to cross the bridge and the output should be 1. We already know how to do that. Write the FORTRAN program to output the appropriate toll for a given user input. R for car, V for bus or truck, B for bicycle. The program should use a select case statement for the type of vehicle. So before proceeding to implement problem 3 in FORTRAN, let's explore it in Mathematica. Let's see, let's plot the functions that were given. The easiest probably is the sum, which results in a constant value. You can see on the plot the sum is a green line. We can evaluate it, get the approximation of this sum. It's 3.21788. It's the quantity that has the least issues, except for that little factorial 20 exponent of -1 over w squared. So it's something that we just did earlier today. Simply invokes the exponent function. The only thing is maybe it will make sense to just test it out to ensure that it actually returns the right value. So we'll put a couple of test values. We'll try the value 1 for w and 1.5 for w. So we have two results that we can also test in Fortran and see if they coincide. If yes, we will consider that we compute correctly. It's actually a more fundamental question. After you code something, does your algorithm actually compute what you intend to compute? It's a difficult thing to test. Here we have an option to first try this out in Mathematica, so this is what we're doing. So for the elliptic integral of the third kind, first of all, there is a Wikipedia article about elliptic integrals. You can read all about them. This is the one that we're looking for, the complete elliptic integral of the third kind. There's nothing to be afraid of. It's a mathematical expression in the form of an integral. It's not really clear for us how to evaluate it, how to get that number. Mathematica can do that. It's not our concern how it does it. In fact, it provides a function name that already contains that evaluation process. As suggested here in the assignment, trucks and buses are charged 10 pi of 0 and w over 10. So that's evaluated here. The only little difference here is that the second argument we need to square. That second argument is k. Note how it is squared over here in the formula. It's a matter of convention. In some cases, some books, they don't square it. The others do square it. In this case, it has to be squared for Mathematica to compute it properly. We also have two test values, one for w equal 5, another for w equal 9. We evaluate these elliptic integrals in Mathematica. Let's do this now in Fortran. We will do in Visual Studio Code, this time in Linux. We already worked in Windows today, so maybe time to go back to Linux. We will split the whole problem into separate pieces. We'll start with the easiest one, the ones for the cyclists. There is a function here that is called series. It computes the sum. It creates the result r. R is the result. There's no parameters to this function. It does something. It doesn't need any parameters. It produces a constant. So there's also an integer for the loop. The result starts from 0 and adds different terms of the loop. We just kind of randomly select 40 terms for now. Whether it's a good choice or not, we will see. At the end of the evaluation, the result is multiplied by -7. This is this -7 over here. Now we do have -1 to the power of k, which is shown right here. And then the factorial. There is plenty of ways to code the factorial. There's many instructions on the internet. It's a very common assignment given to students to write a function that computes a factorial, because it's very easy to make an error. Once you multiply it, the number grows quickly. Once it reaches a certain threshold bigger than the integer can hold, you start getting the wrong results. You still get numbers. You don't get infinity. You don't get not a number. You get integer that kind of wraps around, and you think you're computing the factorial. In reality, you're not. Let's instead invoke gamma function. It turns out It is part of the standard set of functions in GFortran compiler. Let's look at them over here. There's a page, intrinsic procedures for GFortran. It's at the gnu.org website. And there's quite a lot of functions, much more than we previously noticed. There's one that you will need to do on the lab, the function called huge. There is, I think, another called tiny. They have to deal with the real valued numbers. There's also among them, I just scrolled through it, gamma function. And gamma function, it's the real valued approximation of a factorial. For integers, it will give you a factorial, with the only difference is that in order to get the factorial of n, when you invoke the gamma function, you'll need to give it n plus 1. So this is what we do. You can read more about gamma function on Wikipedia if you'd like. We're not gonna pause on it too much. So in order to get the factorial, we invoke gamma function. We convert our 2k integer to real and add 1 to get the factorial. So once 1 is added, it becomes a factorial function. And that's all there is to it. So just one line of code inside the loop, multiply by 7, and the rest is just wrapping of the function. We also have a program to test our calculations. So for now, this is a standalone file. There is a main program over here. Note how you need to redeclare that function. So you already have the function defined on top of the code over here. Inside the program, you need to declare it like a variable, but now it's not going to be a variable, it's going to be a function. So that's the way it works. If implicit none is enabled, if it's not, then this declaration is not necessary. Let's compile. This is the final result. Let's compare to the mathematical worksheet if we got it right. So 3.2178. It seems we got it correctly. Now, we're not talking right now about the precision. Maybe there's an error in one of the last digits. Okay, so it's not our concern at this very moment because it's going to be rounded to the nearest 25 cents anyway. On the assignment, though, you will be given bonus points if you get the answer exactly. You can read about it, how to do this. Of course, if you just compute it the way it's shown in the code, you're not going to get the exact result. You'll have to figure it out. If you don't want to, that's fine. That's a mystery that will not be uncovered. And another thing here, there's a big table. First is just the number of k. The next is the gamma of k. Then we have the inverse gamma of k. And finally, 1 over 2k plus 1. So that's exactly the same expression that we have in this sum. Now, why is it in here? At some point, when k becomes very large, not very large, but just reaches 18, 1 over gamma of 2k plus 1 is 0. There is not sufficient capacity for our real valued variables to hold such, in this case, such a small number, and it just rounded down to 0. So what does it give us? It only makes sense to include 17 terms. So right now I include 40, absolutely unnecessary. 17 is entirely sufficient. What we'll do now, we'll just comment out this test program because we're gonna write the main function later. We don't need a main. Over here, there's a file that contains only the function series. That's all there is. Save it, leave it be. We can compile it into an object file. This is not right now the point of the discussion. So we will not be doing object files anymore. You already seen them. We will delete the executable, and we move on to the next one, which is cars. So the next one, I don't really see how it needs any profound discussion. So this is the simplest formula you can imagine. We already worked with this. We even did this on an ancient 1970s hardware with the old FORTRAN. If there is a necessity, we can test the function just to ensure that it still works. Let's see if it still runs. And it outputs two values, one for like 1 and the other one 1.5. Let's compare it with Mathematica. 7.35 and another is 12. So 7.35 and 12.82. Yes, we get the right result. Similarly, we don't need the test code anymore. In some languages, and I think including Fortran, there's ways to automate these test modules. So you can, for each function that you write, you can write a test module to ensure that it works properly if you know some of the input and output that it's supposed to produce. Now, as for the elliptic integral, so in Mathematica, we have this function elliptic pi, which is kind of given to us by Mathematica. In Fortran, intrinsically, there is no such function. So what you do is search the internet, compute elliptic integral in Fortran. Very quickly, you will stumble across, basically it will be the very first Google link that you will see. Elliptic integral in Fortran 90 code, which evaluates elliptic integral functions using Carlson's elliptic functions. I don't know how it works, but it's important to know what it does. And this is the source code, which is downloaded. The source code will look like this. It's a fairly long file with many different functions. So it starts with elliptic integrals of the first kind, and it continues complete elliptic integral, incomplete, and we search until we find the complete elliptic integral of the third kind. Now we look at this formula. It doesn't exactly match the one that we have, so we keep searching more and more until we find the formula that matches exactly the expression that we're looking for. So this is the function in this library. And also notice how this library is distributed. It's distributed as a source code. So it's not a compiled object file. It's a source code that's open source. It's just given out for free to use. And this is what made Fortran so popular, because people wrote some source codes, even in the past, decades ago, and they still work. Just it allowed Fortran to coexist with languages such as C, because it has like a very big base of open source that was created in the past before C even existed. That's my guess about it. So we'll use the function elliptic pik. All we gotta do is attach it to our code. We will still make the function trucks, which will calculate our output for trucks for a given weight. A little bit of trickery over here. So we'll need, aside from just like the real variables that we talked about, we need the reals that are 8 bytes in size, because elliptic pik operates double precision reals. We will assign the input values to them. So 0, W/10. We will compute the result and then convert it to a normal real that we use. So that's what this function trucks does. Of course, when compiling, we also need to attach the source code that we downloaded. And that's all there is. Compiles fairly fast, so there's no need to split everything into object files and such. It compiles fast until the project reaches a certain size. So let's check the results. So 16.85, 22.80. Exactly the same that Mathematica gives us. Similarly, let's remove the test program and look at the main. So we have this main code, which will use all these functions that we just created. it will use the external functions trucks, cars, and series 1, which computes our constant. Similarly, we have W for the weight, result for the result, and also a character string, just with one character size, of the vehicle type. We'll start with the vehicle weight. This line you already saw a million times. Prints out a string but does not start a new line. Read the value into W. If it's bigger than 9, as the program requests, print out -1. This may be a new function for you, exit 0. So 0 doesn't mean anything, it's just left for the operating system to process if needed. If it's less or equal to 9, request the vehicle type, read it as a 1-character string. As the problem asks, we will use the select case statement. So cases will be R, B, and V, and the result is computed accordingly. So this whole structure is very self-explanatory. One of the 3 functions is invoked. And then finally, the rounding. There might be other ways to do that. There might be some custom written subroutines to do that. Whatever real valued result we had, multiplied by 4. Why 4? Multiplied by 100 cents to get cents, divide by 25. And then round it to the nearest integer, and then convert back to our initial currency by dividing it by 4 again. So multiply by 4, round, divide by 4. This rounds it to the nearest 25 cents. And print out the results with 2 decimal digits. And that's it. So let's compile everything together. All right. And of course, I made a typo. Vehicle weight 10 results in nothing. B would give us a constant. Weight, let's see, 0.1. This will be a cyclist. Look how it's rounded to 25 cents as expected. Similarly, so what test cases we had? We had for the cars 1 ton, car 7.25. So we had 7.35 rounded to the nearest 25 cents, and so on. So you can test it out if you'd like. I did test the code, it works. This is the problem sets given to you on the silver platter, because it's very similar to the problem sets. All you gotta do is just plug in different formula in there, and you're done. I hope you get some idea about programming by following this code with me. We had some new materials today about linking and compiling. Also, there's a new section on Brightspace where there's some PDF materials from last year's lecture. None of that is mandatory. You can scroll through it if you'd like. If not, lectures should be sufficient for you to pass the term test. And if there is something that you see is missing for you to write the problems, please feel free to ask or Google it. All this material is basic. Most of it goes back to 1960s and 70s. So there's no mystery left in terms of FORTRAN programming. So it's all available on the internet. So thank you very much. We'll continue next week. Also remember that there is lab problems are due on Sunday. And there's a lab quiz. I believe it's due tomorrow on Saturday.